Here at HPA, we're no stranger to the Subaru FA20 engine. We've had one of these fitted to our Toyota 86 project car since the day we took ownership when they were brand new. Now, our FA20 hasn't had an easy life either. It's been running around about double the factory power thanks to a turbo kit and E85 fuel. On top of that, it doesn't get an easy life. It's either being beaten up on the dyno or it's being raced around a track with very little road driving in between. So it's pretty impressive that it's held up so well. Of course, all good things can come to an end, and our FA20 is no different. Now, it didn't actually die a horrible or impressive death on the racetrack, as most would expect. Instead, it went out in a fairly subtle way while preparing for one of our live webinars. What we've ended up doing is bending one of the connecting rods, which we've found to be one of the weakest links in the FA20 engine, testing our rolling anti-lag or rolling launch control strategy. Now, this actually doesn't end up doing a lot of damage if you pick it up early. It becomes pretty obvious because the engine starts producing a knocking sound. It sounds a little bit like a run bearing. Given that we've already experienced this with a previous engine, we immediately knew what the cause was. Now, at the moment, we are building a all-singing, all-dancing FA20 engine to go back into our car using forged pistons and aftermarket forged connecting rods. However, while we're waiting for our good engine to be completed, we decided we'd dust off the original engine out of the car with the bent rod and get it up and running so we can still have a bit of fun. Right now, the engine is still a complete long motor, so we are making a few assumptions as to what we're going to find inside, but at this point we are expecting the damage to be confined to just a single bent connecting rod. Of course, there's not a lot of point refitting the engine with a set of factory rods, as we know that these are the weak point here. Despite the high 12.5:1 compression and the fact that we are using a turbo on this engine, we actually haven't seen any weakness or problems with the pistons at the power level we're operating at. It's really just the con rods that have let us down. So what we're going to do here is we're going to strip the engine. We're going to leave the short block assembled, but we're going to be removing the pistons and rods. It's one nice feature with the FA20 design compared to the earlier EJ series engines, is that we can actually remove the pistons and the connecting rods from the crankshaft without needing to break the two halves of the crankcase apart. What we're then going to be doing is fitting a new set of forged H-beam Brian Crow connecting rods. Now, these are going to be well and truly up to the task of the power we're expecting and the sort of RPM range that we're going to be running the car to. This is going to simply future-proof the engine so that we can be comfortable running the sort of power levels we're already running, knowing that the con rods are going to be safe and reliable. Now, in most instances, we can't actually do this that easily. The reason for this is that a lot of factory engines use what is known as a press fit between the wrist pin and the small end of the connecting rod. And this allows the wrist pin to float in the wrist pin boss in the piston. Aftermarket connecting rods primarily use what is referred to as a full floating wrist pin, where there is a bronze bush in the small end of the connecting rod. This means that the wrist pin rotates in both the pin bosses of the piston as well as the small end of the connecting rod. In this case, to stop the wrist pin from falling out of the piston, it needs to be positively located in the piston itself. Now, in the case of the FA20, we're actually quite fortunate because the factory wrist pin is also a full floating design, meaning that swapping out the factory weak rods and fitting a set of Brian Crow forged H-beam rods is relatively straightforward. Now, while we're at it, we will also be fitting a new set of big end connecting rod bearings. We're also going to be fitting a new set of head gaskets, and we're going to be upgrading the head bolts to a set of ARP head studs as well. We'll also be fitting a slightly stiffer set of valve springs, and this again is just going to future-proof us for the point where we may want to raise the boost a little bit further. So with that out of the way, let's get stuck in and we'll start stripping this engine down. Well, we've got our FA20 stripped down to component form. We've removed the pistons and connecting rods, and the problem with the engine, fortunately, is exactly what we're expecting to see. By carefully inspecting the connecting rods, we could visibly see that number 3 rod was quite badly bent. This becomes even more apparent when you take the rods off the piston and you locate 2 of the rods on a common wrist pin. You can very easily see the difference between the 2 rods. Because the bent con rod ends up very slightly shorter than it should be, this results in the bottom of the piston skirt just barely contacting the bottom of the bore at bottom dead center, and this is the noise that was audible while the engine was running. Now, before we just go and put the engine back together, of course we do need to carefully inspect that piston and make sure that it hasn't been damaged. In this case, there is no visible damage or obvious damage to either the block or the bottom of the piston skirt, and this has also been aided by the fact that we knew exactly what had happened and the engine was essentially shut off as soon as we knew that the rod was bent, so there was very little chance of this doing damage. If we're taking the car out on the road and run it at high RPM and full boost, it's very likely that this problem would have become much greater and would likely end up with a connecting rod out through the side of the block. So it was lucky we caught it early. Our plan, as we've discussed, is to fit our Brian Crow rods into the factory pistons. However, there is a bit of a curveball that's been thrown our way here. What we actually can see is that the factory connecting rods are tapered towards the top of the piston, and this coincides with a taper shape to the wrist pin bosses in the piston. What this means is that the Brian Crow rod currently isn't going to be able to fit. Now, that's not necessarily a huge problem for us. The rods are complete overkill for the sort of power levels that we're expecting. So what we're going to do is have our machinist just taper the top of these rods to essentially match the profile of the factory rods. This will allow them to fit into the pistons and it will allow us to reassemble the engine. Of course, the downside here is that we are taking away from some of that strength that the Brian Crow rods provide, but again, because we're not going to be operating anywhere near their limit or their potential, we're going to be more than comfortable with what we're doing here. This is going to give us a nice improvement in strength over the factory rods. It's going to give us a bottom end that we can beat on reasonably hard and be confident that it's not going to fall to pieces. Of course, that remaining weak link there is the factory cast piston. So with a quick analysis of what we've found and what we need to do, we're going to head off to our machinist and get these rods modified to suit.
One eternity later.
We've now received our modified Brian Crow connecting rods back from our machinist, and we can see the modifications our machinist has made. Here we've got our factory connecting rod where we can clearly see the taper at the end of the connecting rod. This has simply been matched to our Brian Crow rods. We've now got a set of rods that will fit perfectly inside the factory pistons. Now, another little tip when modifying a set of connecting rods like this, that modification can actually affect the clearance between the small end bush in the connecting rod and the wrist pin. So this needs to be checked, and in this case the small end bushing did need to be honed to get back to the specific clearance that we needed. So we've got our set of modified connecting rods. It's also worth mentioning here that at this point Brian Crow actually now supply these rods modified as an off-the-shelf item ready to go in with the factory FA20 pistons. So obviously we're not the only people making this change. So if you are looking at doing this yourself, you can save yourself the expense of the added machining and just get these rods directly from Brian Crow ready to go. So now that we've got our rods back, it's time to actually start assembling our engine. One of the important points to consider when we are assembling the engine is to carefully check our bearing clearances. Now in this case we've only been fitting new connecting rods, we haven't actually taken the crankshaft out of the engine block, so our main bearings are untouched. But of course we do want to be very careful and make sure that our big end bearing clearance is where it should be. And this is actually an issue we struck when we were assembling the FA20. And I just want to run through here how we address this, because this is a question we quite often get asked, If our bearing clearance isn't where we want it to be, what options have we got available? So in this case, as we already know, we are using our Brian Crow H-beam rods, and we have fitted a set of King aftermarket big end engine bearings. When we first dummy assembled everything and checked our clearances here, we found that our big end clearances were in the region of about 1 to 1.1 thousandths of an inch. Now, this is a little tighter than what we wanted to run, given the sort of use this engine is going to see. We were really targeting somewhere closer to about 1.7 to 1.8 thou. Now, that doesn't sound like much, but when we're talking about bearing clearances, it really is quite critical. Now, there are a few options available to us in terms of adjusting our bearing clearances. One of these would be to fit a set of graded factory bearing shells, which are available for a number of engines. And these graded bearing shells essentially allow a small amount of blueprinting right from the factory. What we're looking at here is the diameter of the crankshaft journal, the inside diameter of the connecting rod big end journal, and then we can choose graded shells to suit those specific tolerances or clearances and get our oil clearance exactly where we want it to be. In this case, we don't have the luxury of graded bearing shells being available from the manufacturer, so we are dealing with the off-the-shelf bearing shells from King. Another option would be to choose an undersized bearing shell and then have the journal ground by our machinist in order to achieve very exact tolerances and get our clearance where we want it to be. Of course, this adds a lot more complexity because it would require us to strip the engine block bare and then send our crankshaft off to the machinist and have it modified. We don't really want to go to that trouble, but when we checked more carefully, what we actually found is that the Brian Crow rods as supplied had the big end tunnel set to the bottom size or the smallest size of the factory tolerance. That's actually not uncommon with aftermarket con rods and allows a little bit of freedom to manipulate this bore diameter or dimension to get it where we want it to be. Every single component inside a factory engine has a tolerance range which is acceptable, and this is exactly the case with the big end bore and our connecting rods. In the factory manual, we're going to find a top size and a bottom size, and as long as our big end bore is within those two specifications, the part is considered to be good to go. Since our Brian Crow rods were supplied with the big end bore at the smallest size of the factory tolerance range, this gave us the freedom or flexibility to have our machinist hone the big end bore out to the larger size, the top side of the tolerance range, and this happened to give us exactly the clearance we were looking for. Now, this does need to be approached with a little bit of caution. When we are making modifications to the big end bore size of our connecting rods, we do need to make sure that we maintain within that factory tolerance range. This makes sure that we are still providing the correct amount of crush to the bearing shells, and it's going to locate them correctly and make sure that they're not in danger of spinning in the big end bore. So that's just one way we've got at our disposal of making adjustments to the bearing clearances, getting them where we need them to be. So at this point we've got our engine build completed, we've got our new rods fitted, and one thing that I did want to just mention here that became really apparent when we were reassembling this engine is just the complexity of the factory dual cam chain drive system. Now, it's not rocket science here, but getting the cam timing correct on any engine is obviously critical to both having the engine run how it should, as well as avoiding costly engine damage from valve to piston or valve to valve contact. Now, the FA20 FA20 is one of those engines where there is enough complexity in the cam chain design that without prior knowledge of the engine, you're not going to have much of a chance of getting the engine timed up correctly. So this is where one of my key tips comes in. When we're building any engine, it's always a good idea to start by finding a copy of the factory workshop manual. Now, this is going to guide you through some of those trickier operations, such as the cam timing on our FA20, but it's also got a host of other really important information, such as torque settings for all of the factory fasteners, the correct procedure for disassembly and reassembly of all of the components, as well as the correct specifications for things such as the bearing clearances. Now, we quite often get asked, well, that's all well and good, but where do we find a copy of the workshop manual? And here, the good old internet is always my go-to. As long as we're dealing with an engine that's relatively popular for modification in the aftermarket, we should be able to find a copy of the workshop manual in a matter of a few minutes on Google. Now, where this does come unstuck is if we're dealing with an engine that's not particularly popular, or maybe you're lucky enough to be dealing with an engine that is brand new straight off the showroom floor and it's only just come into production. In both of these situations, yes, it can be a little bit tricky because that information may not have quite made it out into the internet just yet. Well, with our engine assembled now, there's only one thing left to do, and that's to get it back into the engine bay. So at this point, we've got the installation of the engine complete back into the chassis. And the next step of the process is the first startup. This is always a satisfying time, regardless how elaborate your particular engine build is. Now, in most instances, with a fresh engine build, we would need to go through the process of bedding in or breaking in that new engine. In our case, though, you'll recall that we haven't replaced the piston rings and we also haven't had the engine block honed. So there's technically no break-in process required here. All we've done is we've replaced our connecting rods and our big end bearings. We will still be starting the engine up here with a slightly cheaper mineral-based engine oil, and we're going to be running the engine up to full operating temperature before dumping that oil. And this just allows us to flush out any of the assembly lubricant that we've used during the assembly process. We'll then be refilling the engine with a normal Motul full synthetic 300V oil that we run in the car, and we'll be ready to hit the dyno. Now, if you had in fact replaced the rings, then yes, a break-in process is necessary. And this is one of the areas where I see a huge amount of misinformation and confusion out there in the industry, mainly around what we're actually trying to do during the break-in process. There's all sorts of concepts around breaking in or bedding in the bearings against the crankshaft, heat cycling the engine, and really all of this is complete nonsense. Let's deal with the bearings for a start. Now, the bearings do not run against the crankshaft. They must be protected by a film of engine oil. And anytime we've got metal-to-metal contact between the bearing shell and the crankshaft journal, we're going to end up with instantaneous damage, and no amount of gentle driving is going to help you in that case. So we're not doing anything in terms of bedding in the bearings. Let's move on to the heat cycling process. Now, I think there's some confusion here between the term heat cycling and heat treatment. And again, this is absolute nonsense. The sorts of temperatures that we're likely to see in our engine when it's actually running are nowhere near the sort of temperatures that are genuinely used for the heat treatment of our engine components. So again, not something that we need to worry about. Really, when it comes down to it, the key aspect of bedding in or breaking in a freshly built engine is really all about the interface between the piston rings and the cylinder wall. What we're trying to do is get the rings to seal against the cylinder wall, and we've got that nice fresh hone pattern on the bores that helps with that process. And this is really critical because if we get our piston rings sealing well against the bores, we're going to end up with an engine that produces good power, good torque, and it's also going to use minimal oil. Now, this process does require a specialized step-by-step approach, and it's important to understand what we're trying to do here. We don't need to baby the engine and nurse it along for thousands of miles. In fact, what we actually want to do is use a little bit of cylinder pressure to our advantage. Now, the radial tension of the rings alone don't really help them to seal against the bore, and the key to getting the rings to seal against the bore or push outwards against the bore is the cylinder pressure above the piston. So when we use a light to moderate amount of load on the engine, using our throttle of course here, this helps push those rings out against the bore and helps them bed. Of course, when they are running against that fresh hone pattern though, this does create a lot of friction, and in turn this creates heat. So we don't want to apply sustained high load, otherwise we could end up with too much heat being generated. So instead what we're going to be doing is using moderate to light load. We're going to be cycling between periods of moderate to light load, and then we're going to be backing off the throttle. And when we back off the throttle, this allows the rings to release a little bit from the bore walls and reduces that friction and of course the heat being produced. And we're just going to be constantly changing between periods of light load and periods of no load. At the same time, we also want to vary our RPM, and at least initially, we're going to be using somewhere in the region of 2,000 to 3,000 RPM, and maybe as much as 30 to 40% throttle. After the initial bedding in process, we'd then start increasing both the RPM and the load. And this process also doesn't take anywhere near as long as most people think. With modern honing techniques and modern ring construction techniques, the bedding in process is usually completed within about the first 100 to 200 kilometers of use. Beyond that, your engine is running, and from here on in, it's all running out. So you might as well get to enjoy it and start using it how it was intended. So at this point, with our completed engine build and our newly installed connecting rods, we're looking forward to hitting the dyno as well as the racetrack with a little bit more confidence that the engine's going to be able to withstand this sort of abuse that we're going to be dishing out to it.
If you like that video, make sure you give it a thumbs up, and if you're not already a subscriber, make sure you're subscribed. We release a new video every week. And if you like free stuff, we've got a great deal for you. Click the link in the description to claim your free spot to our next live lesson.